Welcome to the 2007 Wilderness Lecture Series, Visions and Voices, Writers on Conservation, Wildness, and Nature. My name is Nikki Fear. I'm with the Wilderness Institute, which is one of the sponsors for this series, along with University of Montana's Environmental Studies program. Thank you so much for making the move tonight. We had a sense that we would fill this room and overflow if we'd had it in the Gallagher Business Building. So rather than sending people away, we had to make the move, so thank you for accommodating this change. Our next speaker for next week is going to be Phil Condon. He is an author and an assistant professor in environmental studies here on campus where he teaches nature and environmental writing. We promise his talk is going to be in the Gallagher room 106. If you're a student in the class, you have to wait till the end of the lecture and then come down and hand your paper in. You can just come and bring it to the podium here. We also have books that Janine will be happy to sign for you at the end of the lecture. She's going to talk for about 45 minutes, and then we'll have questions and answers until 8:30. And then there is a private reception that will be at the same location as planned. Now that was so funny. So now I'm going to welcome Bryony Schwan, who's one of the co-founders of the Biomimicry Institute. She is a very well-known Missoula leader, the founder and former director of Women's Voices for the Earth. And she has recently turned her talents and wisdom to help promote this promising field of biomimicry. Bryony is going to introduce Janine Benyus.
Thank you, everybody. I'd like to start out by saying thank you to the Missoulian, to Perry Backus and Michael Gallagher and Sherry Devlin for the fabulous story on the front page on Monday, and to Edward O'Brien for his great coverage on KUFM. Janine and I were talking earlier about how intimidating it is to actually speak in front of people that we know and love and care about, and our neighbors and families. And I recall a while back ago, one of my teachers who said, well, you know when you're nervous, just imagine everybody out there that they don't have their clothes on. So I'd appreciate it if you'd all stand for a moment, remove your clothing, and on the seat in front of you. Make us all feel a lot easier. Several years ago, I made a vow to myself and to many of my friends that I would never again take the job as an executive director of a nonprofit organization. Executive directors work long hours, and when times are hard, it's often for very little money and sometimes none at all. And they lay awake at night wondering when the next donation or grant will come in so they don't have to lay off their staff. Then along came my friend Janine Benyus with a proposal that I couldn't refuse. Would I like to become the executive director of an institute that didn't yet exist and better yet had no money? Well, the lure of battling the IRS bureaucracy for a 501c3 tax-exempt status, wading through other state forms for establishing a nonprofit corporation, and turning over rocks to find money was just more than I could resist. And while I'm joking, or at least a little, I want to tell you why. When Janine started talking to me about the idea of a Biomimicry Institute, I thought this was one of the most exciting projects I had heard about in a very long time. And why this really is the job that I could not resist. I now realize that this is the most important work I'll ever do in my life. For over 15 years, I've worked in the field of environmental advocacy, trying to convince corporations to clean up their act, government agencies to do their job, and dragging a resistant public to engage in issues that are critical, yet daunting and often depressing. Much of the time, we were trapped in the quagmire of advocating for the phase-out of hazardous chemicals and processes, which everyone knew needed to be phased out, even the industries themselves. Yet so often, we had no real alternatives to offer. Or if we did, the alternatives were sometimes only the lesser of several evils. Then along came biomimicry, this amazing concept that actually allows us to make the products we want, or heaven forbid, actually need, and do it in a way that doesn't soil our own nests. Biomimicry helps us find structures, processes, strategies, and mechanisms in nature that nature's been using for over many billions of years that we can emulate and use in modern design. And tonight, Janine Benyus, the woman who coined the term in her groundbreaking book, Biomimicry, Innovation Inspired by Nature, will take you on a journey of inspiration. This woman is a lot like the amazing organisms that she will show you tonight, in that we don't often recognize the genius right in our own backyards. The irony is that Janine's work is internationally known, yet there are still so many Montanans who don't know about her or about biomimicry. I first met Janine 20 years ago, shortly after we both moved to Montana and the Bitterroot Valley. And I was immediately taken with the warmth and the joie de vivre of this young woman. Remember when we were young, Janine? Yes. At that point in her life, she had already authored 4 natural history books. And over the ensuing years, I watched her life change as she authored her next 2 books. I'm not sure she, or the rest of us who know and love her, were prepared for the changes that biomimicry would bring. Soon after the book's publication, she began to receive invitations to speak from all over the world. Then followed the deluge of companies who wanted her to assist them in developing new products and processes using biomimicry principles. Ray Anderson, CEO of Interface, the world's largest commercial carpet manufacturer, invited her to serve on his dream team. As a result of working with Janine and her team, Interface introduced Entropy, a carpet inspired by the random pattern formation in nature. In record time, Entropy rose to become Interface's top-selling line of carpet. 4 years later, this biomimetic product represents 40% of their carpet tile sales. Interface carpet uses a fraction of the raw materials other carpet manufacturers use, and Interface's goal is to wean itself from oil and manufacture carpet entirely from bio-based materials, taking back its old carpet and recycling the material. You know, I often call Janine to meet up with her for dinner or go for a hike, only to find out that she was in Japan talking with the government and Japanese investors about biomimicry innovations, or that she was in South America attending the opening of a new university modeled on biomimicry right in the heart of the jungle. So I'd wait for a few weeks and I'd try again, but it didn't make any difference. She was always somewhere doing something extraordinary. Paul Hawken, entrepreneur, businessman, and author of many books, including Natural Capitalism, says that Janine is without question the world's most imaginative person in the field of environmental development and restoration. To be with her indoors is to be transported. To spend time with Janine outdoors is like walking through the looking glass of extraordinary beauty and landing in a meadow of possibilities about our world. Time spent with Janine is a transmission of hope about what we can learn from and be within nature, a species of hope that will follow you for the rest of your life. So to respond to this outpouring of interest in biomimicry, Janine and her colleague, Dana Baumeister, established the Biomimicry Guild in about 1998, a consulting firm based in Helena. Clients now include many large and small companies, and here are just a few of the biggies. Consortia, General Electric, General Mills, Gensler Architects, Herman Miller, Hewlett-Packard, Kohler, Levi's, NASA, Nike, Seventh Generation, and SEC Johnson. And I could go on and on. But companies are not the only ones who sought her ideas and inspiration. Almost daily at the Institute, I receive calls asking for Janine to keynote a lecture in Asia, Europe, or almost anywhere in the world. Prince Charles and his wife Camilla invited Janine to spend a couple of days with them and their staff in Balmoral Castle. He's a huge biomimicry fan. Next month, Janine will visit with ministers of European Parliament and then the King of Sweden to discuss climate change solutions. Everywhere she goes, Janine inspires people with a message of hope in a world that faces extraordinary environmental challenges. It is this message of hope, it is this method of hope that inspired me to join this extraordinary team. Frankly, I can't wait to go to work in the morning. Finally, on a personal note, I'd like to say something about the person of Janine Benyus. One could imagine that someone who's received such international attention and recognition for her work might let it all go to her head. But to the contrary, despite her phenomenal contribution to the world, she remains a warm, fun, and remarkably humble human being. And every day I thank my lucky stars for the opportunity I have to know and work with this amazing woman. It is my pleasure and honor to introduce you to Janine Daniels.
Brian, God. Oh, I've got this. How lucky am I? To have these kinds of people in my life. If there's one Montanan out there who does not know about biomimicry in a year, I will be surprised. Because Bryony is on the job. I met Bryony. Bryony's my oldest friend in Montana. It's the first person I met in Montana. And she has taken me down many a whitewater river, and those of you who know me know that that's not always the easiest thing for me. I love to row the quiet stretches. And I will row the quiet stretches, and then when the water starts quickening and my heart starts pounding, it's time to look for Bryony. And to hand the oars to Bryony. And to have her capable hands. And that eye for pattern bring us back into the quiet spot again, with an awful lot of fun on the way. And that's what I expect our years together to be like in this. I feel very fortunate. What are we doing?
I'm so sorry.
Oh, were you trying to? Yeah, I'm kind of a trance baby, as you'll see. Anyway, Bryony. Here are the oars. Let's have fun. She's right that it's a little bit nerve-wracking to have your friends and family in an audience like this. I'm lucky, though. I'm lucky to have my lifelong rowing partner, Laura, here, and to have my...
Janine,
Yeah.
you still cut hair in the back?
No. Oh, shoot. How's that? Well, that's like if I hold it here. Or like clip it to my nostril. I hope this is being televised and will live forever. This is what I'm hoping. How about if I'll just hold it, guys?
Perfect.
That's fine. All right. Anyway, where were we? I was telling you what it's like to look out and see my rowing partner, Laura, and my father is here. And which I don't often get to have. And he taught me about wildlife. And he taught me that it's not one word. It's two words, wildlife. And it can be a wildlife if you put wilderness and the wild at the center of your life. You're assured a wildlife. So Dad, I'm really proud to have you here. And I have lots and lots of my gaggle of friends here. I have a great flock to fly with. And every time I look around, I'm going to see somebody new. How many students are here? Raise your hands. Oh, good. Oh, good. Because you really do fly in a flock. And like birds, you're not always the one leading it. You take a break and you let the fresh birds come to the front. And it won't be long at all before we tap you on the wing and tell you that it's your time. And I just want you to know that you are not alone. There'll be the other birds, many of which are in this room. But they'll be the actual birds that when you look up into the Montana skies and you see them returning now, those are the ones, those are the elders that are going to lead your to keep your eyes on them. Tonight I'm going to talk about biomimicry. And what I'm going to try to do is tell you what we're doing now, what the latest is, because it has been quite an amazing transformation. As Bryony mentioned, when I wrote the book, I just went and started to write my next natural history book, and the phone started to ring. And it was people like Paul Hawkins saying, no, why don't you come and start to work with the people who are designing our world, the people who are making products, and chemical engineers and architects, and the people who make the world that we live in. Why don't you go to them? Because they're interested in making our world more lifelike. But they don't know any biologists. And they don't really know how life works. Why don't you go as a biologist and sit at the design table with them and tell them how life works? And so a new career was born, this biologist at the design table career, which I would invite all of the students here to consider. It's a really, really fun career. And one of the main things that we do, Dana Baumeister is the co-founder of the Guild with me, and one of the things that we do, the first thing we do, is get people outside. It's essential. And we get people outside in their local habitat, if we can. Everybody should have a local wilderness right outside the door so that they can go out occasionally and remind themselves of the codes of conduct, of how to live well, how to live gracefully in that bioregion. So we take them outside. And we were, one of the last trips that we did, we went to Vermont and we went to 7th Generation. And we had the whole company, there are 52 people in the company. They make biodegradable detergents and toilet paper, really good, they're a great company. So we had the whole company there, including Jeffrey Hollander, the CEO. And we brought them to an Audubon Nature Center, and we did a biomimicry workshop with them. And it was kind of embarrassing because they make cleaning products. And no matter where we looked in the natural world, when we went on our walks, we didn't find anything in the natural world besides us using detergent. It was kind of, it's a little risky. It's like we're one-time consultants, usually. That's not true, because they actually have somebody on staff called the Director of Corporate Consciousness at 7th Generation. And they hung with us, and they said, okay, well, tell us about how nature cleans. And one of the things, let's see, am I going to be able to, okay. We were able to show them that many things in the natural world need to stay clean, including leaves, eyes, skin. It's actually a survival imperative to stay clean. So we showed them leaves. There was a great beaver pond there, and we were able to show them some lily leaves. This happens to be a lotus leaf. But what we showed them is that the leaf is a self-cleaning structure. And they kept saying, no detergent? It kind of dawned on them throughout the day, no detergent? And I said, well, surface tension is really pretty important in the natural world. And surfactants or detergents break up surface tension. Oh. It was kind of it dawned on them slowly. And, but what we showed them was that this leaf and many leaves, they clean themselves with rainwater. And the way they're able to do that is that they have a bumpy surface, really small nanobumps. And dirt particles, instead of adhering, just teeter on the tops of those mountains. And then you've seen dew in the morning on a leaf. Water balls up, and as it rolls off, it picks up those loose dirt particles. And that's called the lotus effect. And you'll see that right now. You can paint your house in lotus and paint, and it has a bumpy surface, and rainwater will clean the side of your house. There's no lotus leaves in it. It's just the structure. It's the blueprint that we're learning from. So 7th Generation said, well, maybe in 5 years we'll be beyond the spray bottle. Maybe instead we have a new kind of business. Maybe our business is to create a self-cleaning surface, a material that allows you to just clean with water. Maybe our job 5 years from now will be cleaning water, because that's the detergent that we'll be using. So this is the kind of thinking that goes on. After the first day, they were so excited. Even people like seventh generation don't get out much. We are so lucky in Montana to have this amazing school, and I mean the wilderness, right outside our door. They didn't want to leave the Audubon Nature Center. But I said, no, let's have the second day of the workshop back in downtown Burlington at your office. Because I think the important thing to remember is that not everybody has access to wilderness, but there is wild, and by that I mean wisdom. That's equated with wisdom for me, all around us, even in downtown Burlington. So we went there, and sure enough, we had a great time finding the little green spaces around their building. And one of the things we found was this guy. Now, if you want to see wisdom in an invertebrate form, stare into the eyes of a praying mantis sometime. There's a reason so many cultures saw them as holy. Amazing organism, amazing poise and grace. And one of the employees brought him in. And we were in the cafeteria, and we let him crawl all over us, and he sort of graced us with his presence for a while. And then it was time to take him back out. And I took him back out of my hand, and I instantly saw where he should go. It was this little cedar, and it was exactly the same color as him. He even had a little orange from last year's growth that had died back. And when I put my hand next to that cedar, he melted and disappeared in plain sight. It was beautiful. And I came back in, and one of the employees said, "Why do you think that praying mantis visited us today?" And I said, "I don't think the praying mantis visited us today. I think the praying mantis is always there. I think what happened is that you started to see the praying mantis. And that is perhaps the most important part of biomimicry, is that it truly changes our relationship with the natural world. We begin to see other organisms through a lens of respect. And hopefully, as I talk more about it, you'll start to have that experience as we sit here, and maybe someday we'll go outside together." Oops. Oh, let's see. There we go. I'm gonna show you some people that are involved in this, because they're a merry troupe, and they're great people. This is Peter Steinberg. Now, say you're a student and you're thinking about, what's worth doing in the world right now, and you want to study an organism and you want to tell the world about it. I say do that. That's what Peter did. He was born in Brooklyn, and so of course he became a marine biologist. He loves to dive, he loves coral reefs, he lives in Australia now, but he has a different set of eyes. And what Peter did when he was diving off the coast of Australia, he noticed something. He noticed that in the algae, this is a story of a boy and his algae. The guy loves algae. I just spent a week with him. Algae. And he watches very carefully, and what he noticed was that many of the algae had bacteria. They had slimy biofilms on their surfaces. And biofilms are the dangerous bacteria. That's where bacteria get really nasty. When they get into a biofilm, that's when they turn on their toxins. So in hospitals, when you hear about superbugs, they're living in biofilms. So Peter noticed, oh my gosh, there's this one red algae that doesn't have any biofilm on it. And he asked why. Biomimicry is a deepening conversation with a wise organism. He asked, why doesn't it have biofilm on it? And what he found was that the red algae is doing this amazing thing. It is interfering with the communication signals of bacteria. Basically, bacteria are constantly talking to each other. And when they're floating around, a few will land and then call the others down. And when they get a quorum, it's called quorum sensing. When they get a quorum, they start to form this sugary, slimy layer, and they start to turn on their toxins. But if they can't talk to each other, they don't land and form the biofilm. They just land for a while and then leave because they don't have their buddies with them. So Peter studied this algae and found out what it was doing to interrupt the communication signals. It's just a little molecule called a furanone. And you may be looking at a guy, I was at, having a drink with him on the last night, and I said, am I sitting with Linus Pauling? Because what we're talking about here is a completely new way to deal with disease-causing bacteria. It is a pretty big deal. Of course, it's new to us, but it's very old hat to the seaweed. And so what he's now able to do, he's mimicked the furanons. He's not harvesting the algae. Important point about biomimicry, it's not about harvesting the organism for a product. It's about learning about these furanons. He mimics them, he makes them, and now he can make a cleaning product, for instance, that... Are we having more problems?
Can you try it again?
What? Okay. Can I just keep talking while you play? Okay. Anyway, you can create basically a shield on a surface that repels bacteria, that keeps it from landing. Now, the important thing about that is that it doesn't kill bacteria. When you kill bacteria, you encourage them to become resistant to whatever you're killing them with, like an antibiotic resistance. We also use a lot of harsh chemicals, a lot of chlorinated compounds to clean surfaces. And then bacteria eventually get pretty used to that. So this is a completely new way. It's a very subtle and a keto way, because it repels the bacteria by just confusing them, kind of jamming their ears as they pass by. The company is called Biosignal. I'm going to be putting the company names down here to let you know that this is actually happening. So even if you've heard these case studies, I'll be telling you about new developments that are going on. This is a really important one. You know the pipeline, the BP pipeline that just leaked oil into Alaska? That was caused by microbial corrosion. Microbially caused corrosion, I should say. So if you're able to coat the pipeline with this, you're able to keep bacteria from causing leaks in the pipeline. There's a lot of things that, if you start thinking about it, that this would change. So there's Anwar. These are where we find, as we're despoiling these areas, we really are despoiling the universities, the fine universities. We are surrounded by genius, even in downtown Burlington. Let me tell you about a few brandy new ones that are pretty exciting. There's let's see if I can get, yeah, there we go. This is an electric eel. Very cool creatures. 600 volts of electricity generated instantaneously. No lead, no cadmium, no mercury. 600 volts is a lot to be able to call up at your command. So the eel is now finally being studied for a new kind of battery, a biobattery, a battery that basically would use organic material instead of the heavy metals in order to generate a charge. This is a pretty exciting one. Those are wild grapes. And they have a lot to teach us, not just when they're fermented. Even before fermentation, amazingly enlightened. Anyway, lots of plants do this. Well, let me back up and tell you the problem statement first. The problem statement is fire retardants. It's the stuff that, unfortunately, all of our products are soaked in this chemical. It's a brominated compound. It's a neurotoxin. And so we don't burn to death, but there is a trade-off. And it's fire retardants. And they're in everything, absolutely everything you're touching, I'm touching right now. And they're getting banned in Europe and other enlightened places, and here soon, too. Anyway, so what's the alternative? Well, actually, this is something that happens in your own cells. You know, remember the Krebs cycle? Citric acid cycle? The Krebs cycle, they're mimicking that right now in something called a molecular heat eater that just won a major innovation award because it's an alternative to fire retardants. And it's based on the Krebs cycle. It's edible. The stuff is edible. You can put it on a substance, and what it does is it sucks up heat, molecular heat eater. When it starts to burn, it actually sucks heat away from the area, it sucks oxygen away from the area, and flames need oxygen and heat. And it cools the area so that the flame starts, it chars the outside, and then it stops. That's a biggie. That's a really, really big one. And they're able to, in this case, they're able to take it from the waste citrus from winemaking operations. So drink more wine. This is the toucan, and I just love them because we teach in Costa Rica too, and it's amazing to see these relatively small birds compared to their beak. And you wonder, with a beak that size, that has to be really heavy duty to break open seeds, and it must be so heavy, and yet it's not. In fact, it's incredibly lightweight. Inside there is a porous structure that now is being mimicked for building materials to make them super lightweight for both for shipping and just to not use as much material as we use now. Let's see. Oh, this little guy in here is a tree frog, also from Costa Rica. You know how their pads are amazing. They can jump from leaf to leaf and grab a hold. And those Continental Tire is mimicking the pattern on the tree frog's feet to make safer tires. Let's see. Oh, this guy here is a crested auklet. And every 15 seconds, someone in the world gets malaria. And so there's a big, the holy grail is to find a way to repel mosquitoes without having a chemical that basically eats through your skin like DEET does. The crested auklet breeds on islands off the coast of Alaska in large groups, and there are clouds of mosquitoes around them, but no mosquitoes landing on them. Another one of those biomimicry things. You figure out what you want to do, and then you look for the critter that's doing it really well. Turns out that it has a mosquito repellent that is equal to none. This little guy is a water bear. It's a tardigrade. It's in your drinking water. It's everywhere. They're everywhere. One of the cool things that they can, it's very blown up there. Don't worry. One of the things that it does really well is dry up and then hang out for hundreds of years, a couple hundred years, and then kind of you pour water on it, comes back to life. Well, it's been alive the whole time, but it gets into a desiccated state. And here's another really interesting third world first kind of an invention. What happens is it protects or preserves its cells with this sugar called trehalose, a particular kind of sugar that takes the place of water. And it's kind of a glassy amber material. And a guy named Bruce Rosner of Cambridge Biostability has coated vaccines with this, like tiny time capsules of a mimic. They're not harvesting these guys again, but they have coated vaccines. They're able to put vaccines in a vial of inert liquid and put it in a glove compartment of a car. Now, that's a big deal if you're somebody at the end of what they call a cold chain, because a cold chain is a vaccine's created, and we may be real interested in this one with avian flu coming. The beginning is the vaccine comes and it has to be refrigerated, and then it's put on a truck, and then it's put on a ship. If anywhere that cold chain breaks, the vaccine goes bad. This does away with that completely. There's also a resurrection fern in the American Southwest that does the same thing that he also studied. You wonder why biodiversity is important? Here is hippos, and there's also a lot of chemicals on your, especially commercial furniture and stuff, for UV resistance. Well, these guys, when their tender little skin comes out into the sunlight, they kind of start to turn a tinge of red. And what it is it's sweat. It's called red sweat. And it has a long chemical name, and that chemical is a UV resistance chemical. Now again, we wouldn't be harvesting hippos, we would be mimicking the recipe. Basically, we swap recipes with these guys. This is a tick, and I have searched long and hard to find something. And once you look, there's so many cool things that I even kind of like ticks now. There's a company called Evolvatech that is, what happens is when a tick, if you're squeamish, you may want to leave the room. A tick may be on you for 20 days or so. And the reason is that they're able to calm your defense mechanisms. So your histamine defenses, and they calm that so that you don't know they're there, so that they can get a good long drink. And the way they do that is now being mimicked to overcome autoimmune type diseases. Very, very interesting stuff. The other thing about ticks, and this is one of the students in one of our workshops figured this one out, doing a little bit of research. They were trying to, their job was to create a reusable packaging bag where you could fill it with product, and then it would shrink down to a very small size and be very easy to ship back and be reusable. And they went to the tick because it's a small thing, but it gets really large. Turns out that the plastic-like exoskeleton has these amazing coils that just allow it to expand. And again, that's an inspiration for a package designer. You just wouldn't let the marketing department know about where you got that one. So here's dolphin, and I could go on all night about what we could learn from dolphins, but the latest one that I find really interesting is that we want to transmit telecommunications, computer messaging, for instance, under the water, and it's really tough to do because it bounces around in water. And a company has, in fact, the company was, it was started by dolphin researchers. And they found a way to hook up modems and to mimic the way that dolphins chirp to one another. And they're able to chirp, and they're able to move their messages through quite a bit of water. So your next email may be sent via dolphin chip mimicking modems. Anyway, it's every day there's something new, and so take heart. You know, there's plenty of bad news too, and so take heart that we are surrounded by genius. 3.8 billion years of R&D, 30 million species is what we're figuring. Some people say it may be up to 100 million. Well-adapted solutions. That's well adapted to life on Earth over the long haul, which is a really good measure of success. So as you listen to the rest of these, ask yourself, if you were to walk outside right now and ask nature one question about a problem, a design problem in your life or at work, what would it be? Or something that you know the world needs, really needs. Because this is a big question, I think, especially when I talk to university students. What's worth doing? Laura, I'm going to tell the story when we went up Sweeney Ridge, like the last warm day of the year. And it was one of those hazy, warm, sunny days, you know, and when you can still pretend it's summer, but it's really not. And we went up Sweeney Ridge, and then there are those gigantic big ponderosa pine trees that are still there on the ridge facing south. And we leaned up against these. And we were the laziest organism in that forest. I mean, bar none. Because everybody was in movement around us. Because they were getting ready. They had something worth doing. I mean, these guys, the arboreal squirrels were all over the place. I mean, there was one that had this enormous mushroom, came up beside us. We had to like lift our legs and let him go through because he was like, look, I got things to do and places to be. What I admire about organisms is that they have a purposefulness. They know the weather's changing. They don't deny it, they know it. And they know what to do next. And so as a species, I think what we need to develop is a common purpose, a common agreement about what's worth doing. This is an interesting picture. That little ball on the left that's on the Earth is all the water, all the ice, all the seawater, all the rivers, all the fresh water, every bit of water. That's how much it is compared to the Earth. It's not very much. And that little ball is all the air. Atmosphere, all the atmosphere that we can live in. It's not very much. What's really interesting about it is that it wasn't there, especially that air, wasn't there in that kind of a form billions and billions of years ago. Life helped create it. Life helped create the conditions conducive to life. And in a very short period of time, we're not really caretaking it very well, these little balls. But that's our job. That's as clear a statement of our job in the next century as I can figure out. This is what life does. Creates conditions conducive to life. So that's what we're hoping to do here. That's Adam Neiman. If you want to get that, there's a great article about it where he got all the math. It's a website. So what I'm going to talk about is what's on everybody's mind, which is the answer to Al Gore's great movie. Well, what are we going to do? It's got to be at least a 60 times reduction. 60 to 80 times reduction of what we're emitting now. And so I want to look at how biomimicry might help us stop exhaling excess carbon dioxide at such an amazing rate, and how it might help us start powering ourselves in ways that don't release as much carbon. Is that okay? Everybody's kind of searching for that climate change answer. One of the things that's really important is reducing energy use in buildings. It turns out, and this surprised me, you know how you always think that maybe cars are the cause of greenhouse gas emissions? And they, of course, have their part. Buildings, 48% of all greenhouse gas emissions are buildings. They're coming from buildings. They're coming from the building of building, the construction of building, the operating of building, the tearing down of buildings. So that's a big one. 75% of all electricity, buildings. Not industry. How you kind of, that turned it around for me. So if we get buildings right, we get a lot right. And you guys all live, when you're not blissfully outside, in buildings. One of the things we use a lot of energy for is pumping. 6% of all electricity is used for pumping. Now that doesn't sound like a lot, but only 15% of electricity is used for air conditioning. So pumping's right up there. And one of the things we do is we pump water different places. And it's another one of those things that we could use a lot of help with. Organisms, and we pump water out of the ground. And you don't really see organisms doing that. You don't see them digging big wells, getting that big pump, right? You don't see them doing that. And yet, obviously, they need water. They drink it from groundwater, of course. But another thing that they do that we really haven't thought much about is they drink it out of the air. There's a lot of moisture in air. And if you live in the southeast, or if you've even visited there, you know that there's a lot of what we would call excess moisture in the air. This guy is the Namibian beetle that they talked about in the paper. And here's a picture of the bumps. What he does, he lives in a desert that has no groundwater, but there's a fog that comes in 6 times a month, 50 miles an hour fog. And he lifts his wing scales up, and there's a surface chemistry. There's a water-loving tip on those bumps and a water-shedding side, a waxy sides. And so the water builds up on the tips, and he has his wing scale up like this, and eventually it gets bigger and bigger, and then gravity takes over and it goes down into his mouth. Very simple idea. So finally, there's a company that called Kinetic that is making sheets for the sides of desert refugee camp tents, and now for buildings that basically grab water out of fog, and the important thing is it grabs water and then it moves it away, okay, for irrigation or maybe at some point for potable water, for drinkable water. So think about, at some point, the surfaces of our buildings, you know when it's foggy in Missoula? Imagine getting, the way we think about gathering rainwater now, imagining gathering fog. And inside a building, imagine gathering water vapor. There are insects also that drink water vapor. This is a schematic of a building, a theater called the Water Theater in Spain. And it's on the coast. And the whole back of this amphitheater is coated with that beetle bump mimicry. And it's gathering water and moving it away. Okay, gathering fog. The other thing that in buildings that we're using a lot of electricity for is, well, just listen. Fans. Fans, once you start listening, it kind of drives you crazy. But there are probably a dozen fans that we could count. And they're making noise, and the noise is friction, and the friction is fossil fuel use. So how does nature deal with flow smoothly without friction? Well, there's a shape, and it's called the logarithmic spiral. And it's what you see in hurricane clouds, and it's that's actually a museum staircase. But it's exactly the same as what it looks like, your skin pore looks like. If I was able to get an SEM up on that hand, you'd see a skin pore that has that spiral staircase because water vapor is escaping without friction in that shape. So finally, somebody is making fan blades that have that shape. This is Jay Harmon, another fabulous Aussie. And these fan blades are, I mean, it's the first real innovation in propellers in a very, very long time, or air handling fans. So what we're talking about is computer fans is their first product, and range hoods. You know those kitchen range hoods? God, I hate those. And then they're going to be in air conditioners and in cars. This saves 30 to 70% energy, depending on application. So say 50 to be conservative. 50% energy savings and 75% quieter. That's a lot of fossil fuel right there being saved. If you changed out, you know, a tanker, an aircraft, an oil tanker in the ocean, it gets per mile, per gallon, how many miles do you think it goes? 12 inches. I'm not kidding, it's scary. But anyway, but it's got all that oil that it's carrying, so good thing. That's Pax Scientific. Terrific, terrific company. Organisms build huge structures relative to their size, and they ventilate them without carrier or train and no fans. And the way they do it is these are termites. They keep their mounds at 87 degrees Fahrenheit, and they do that by building all these tunnels, and air comes in, and they live down in the mud, in the cool mud, and they're farming fungus there. So they need to really regulate that temperature. And so the air comes down and it gets cool, and then the chimney stack effect takes it up. very, very cool idea. Here's an architect who went outside his own door and used them as a model. This is in Zimbabwe, in South Africa. It's a building with no air conditioning. It saves the tenants quite a bit of money. It's based on termite mounds. Now, there's a lot of natural ventilation buildings going on right now, and there's a very cool study going on. Here's the update on this. This is Rupert Soar and his buddy there, and they're standing in front of a termite mound. And when you put plaster of Paris into those tunnels, that's what the tunnels look like. And so what they're doing, it's a study called Termes, and it's at Loughborough University. What they're doing is they're taking the first ever slice-by-slice MRI scan of a termite mound, putting it into a computer, because it does more than just do the temperature. It's regulating humidity. It's breathing. It's literally doing this tidal breathing. It's a lung that's sticking up in the air. Imagine thinking of our buildings as extended organisms, as Scott Turner says. So they're going to take this slice by slice, put it into a computer, and figure out if there's something special about the shapes of the tunnels, and then put those kinds of tunnels in walls to help with ventilation. Another thing, if Sandia National Labs just did a study and said that if we went to solid state lighting, if we went to LED lights, you know the little LED lights? That's called solid state lighting. If we went to that, if we only went to half of that, half of our lighting in LED lighting, we would save enormous amounts. The calculation for the United States is as much energy as 200 nuclear power plants. So lighting is huge in this whole question. Now, what's interesting is that butterflies invented LED lighting. They have this thing called Bragg refractors in their wings, and it basically shoots the light out and amplifies it, this fluorescent light. This is Peter Vucevic's, who studies that. And it works a little bit better than the LED lights we have now. Transport. Here's the whale. These organisms do what's called bubble feeding. And so they have to be incredibly aerodynamic. And one of the ways that they come up through the water and they spin around in a spiral, logarithmic, as a matter of fact. They spin around in a spiral, and they're exhaling bubbles, and there's a cylinder of bubbles, and that holds the krill in, and then they go back down and they come up with their mouths open and they have a great party with their buddies. It's a cooperative endeavor. Anyway, in order to be that maneuverable, they depend on these scallops on their flippers. And the scallops, there's a guy, and I can't make this up. His name's Frank Fish. There's a lot of this. This is a mammal, but still, it's kind of funny for some reason. Anyway, he put it on an airplane wing. He put the scallops on an airplane wing versus a smooth one. 32% drag reduction. That's a lot of fossil fuel. So see what's these simple, and they have a company now called Applied Fluid. This is a car, a Mercedes-Benz car that gets 70 miles to the gallon. It's still a concept car, and it's based on this crazy boxy fish called the boxfish, aptly named. And it doesn't look very hydrodynamic, but it's as close as you can get to a teardrop shape, but it doesn't look anything. You can get a family of 4 in here, whereas you can't really in a teardrop shape. So this is Mercedes-Benz. And the other thing that they've done, which is really interesting to lightweight the car, is use a software program based on how your bones work. Because your bones beef up where they need to beef up, where there's stress, and they take stuff away where they don't need to have material. And there's a software program that actually allows engineers to do that. They were able to take 30% off the weight of this car by doing, see how it kind of looks bony? That's a really optimized shape. Now, back to the people involved in this crazy profession. It's a lot of fun. This is Klaus Mathek. Andy, remember I gave you that book? This is a guy who has studied bones and trees all his life. He's taken pictures of trees that have knocked down and then come back up phototrophically and looked at the reaction wood and figured out how trees distribute stress along their surfaces. And that's his bulldog. Bulldog down there, Klaus up there, although... Okay. Manufacturing. This is how we make most things. We heat it up. We beat it with pressure because we had cheap oil. It was never cheap. Illusionarily cheap oil. And we treat it with chemicals. That's how we make materials, but that is not a good way for an organism to operate. So the way organisms make materials like this spider, that's spider silk coming out of the abdomen of a spider. Isn't that beautiful? Ah, see? That's a nice sound. It's the sound of respect. That silk is made from common raw materials, locally procured, right? And I like it, like you just build the web and then you can hang out and it comes to you. I love that. Locally procured material. Chemistry is done in water, which our chemistry is not done in water. Very low pressures. And when you're done with the, if nothing's flown into the web, you can eat the web to make more web. That's chemistry. That's nature's chemistry. Anyway, but you can't, since you're doing it near your own body, you can't heat it up. Okay? So even if you're that's the inside of an abalone shell. If you're a mollusk and you want to make a shell that's twice as tough as our high-tech ceramics, you still can't put yourself in a kiln like we do. So the rest of life has learned a new way. And we're starting to mimic how ceramics are made, how fibers are made. It's this thing called green chemistry, and it's a very, very exciting field. This is Jeff Brinker, who's now making these amazing clear, optically clear glass structures that he basically dips in a liquid, and the liquid evaporates away, and the material, the hard glass, self-assembles into place by mimicking the abalone. Computers, silicon, all the diatoms, all the organisms that have glassy shells in the ocean, we're now mimicking how they make their glass. And Corning, memo to Corning, try to put your kilns on Craigslist, because you're not going to need them. There are some very, very large investment firms obviously looking at this one because of the computer interest. And these are the characters that are working on it, Joanna Eisenberg and Dan Morse, and they're holding a sea sponge, the skeleton of a sea sponge, Venus sea basket, that is a single crystal of glass that self-assembles out of seawater silently at room temperature. The other thing we're going to have to do, besides sipping energy, reducing our energy thirst, is go to the sun. Just straight to the sun. This is a guy named Tom Moore who taught me everything I know about how life turns light into life, plants, and how they gather solar energy, and he's still teaching me. And he's already mimicked what goes on inside a leaf to make very, very small solar cells. Someday you'll be able to spray on a roof. And now he's teamed up, there's many, many people doing what's called artificial photosynthesis as a way to look at our energy issues. There's a big, big team of people doing this now. Pretty exciting. Here's what you can buy today that's based on photosynthesis. That's how plants pull down sunlight. These are thin film solar cells. They're solar cells that you print out like you print out screen printing, and you get rolls. You can see the rolls there by a company called Canarca. They work like leaves do. They use dye to pull in the sun. They're dye-sensitive solar cells. They're not as efficient, but they're 5 times cheaper. And that's a conservative estimate. They also work really well in low light, including indoors. And they work well on vertical surfaces. And they can be made transparent so that your windows can be solar cells. But you know, there's really nasty stuff in PV solar cells, but there's not in leaves. This is a third world first project by a woman named Sheila Kennedy. And this is, I didn't tell you, back to the solar cells, they're now making them, they just hooked up with a fiber manufacturer, and they're putting the solar cells in fiber, so you can start to think about tents gathering their own energy, or any sort of like the membrane above Caras Park or whatever, having its own energy. And you can also think about projects like this, which Sheila Kennedy is combining dye-sensitive solar cells, mimicking plants, and LED lights, and making reading blankets. All day long they absorb the sunlight, and then they give out light with this really, really energy-sipping LED lights so that people can read at night. Reading blankets. What we research is what we get. And if we want stuff like this, we have to support the research that goes there. Fuel cells are really expensive right now. They use platinum. See, life doesn't really take light and put it in wires and do electricity. Life takes light and stores it in a chemical form. Stores the energy in a chemical form. It turns it into chemistry. So we have to find a way to go to the sun, but then turn it into chemistry. And one of the ways to do that is to store the energy in hydrogen and to breathe that hydrogen gas into what's called a fuel cell. It breathes in oxygen, it breathes in hydrogen, and out comes hot water and electricity. It's a pretty cool thing, but it's expensive. The chemistry that's being done, the membrane has this stuff on it called platinum it's the catalyst. This is the cyanobacteria, one of the oldest bacteria that we know of. I mean, these are ancient truths. It does the hydrogen chemistry just fine. So by mimicking the enzyme that it uses, they're able to do very, very inexpensive fuel cells. Still in the lab, but stay tuned. There's a fuel cell you can optimize. Since the fuel cell's a breathing apparatus, what better than to look at lungs and how lungs breathe in oxygen? So when they put the branching fractal shape of lungs into a fuel cell, it increased the peak capacity by 16%. This is Morgan fuel cells. So you see how biologists are starting to sit at the design table now. It's a really interesting. This is Jim Barber, who looks like a very nice man to me. And he's studying the way that leaves, where are we going to get our hydrogen? Right now we're getting it out of petroleum products, natural gas. We'd like to get it out of water. And plants do it all the time. The light comes in and they split water, hydrogen, proton, and then it can combine into hydrogen. So we need to know the little enzyme that does that, and we haven't known what it looked like, except Jim has figured it out recently, which is really good news. He's in London, Imperial College. Then, there's a lot of other kinds of solar energy, or renewable energy besides solar. Here's a great one, again from Australia. There's something in the water over there. It's called Biopower. It's a small little company, and they're mimicking the way kelp move in the ocean, and they're getting energy from that movement. And even in a storm, the whole wave, I think they call it biowave, the whole thing will flatten down so it doesn't get ripped up. And it actually uses a holdfast. It mimics the holdfast of the kelp. And then that's a tuna tail. I mean, the mimic of a tuna tail. for renewable energy. And then, of course, people are talking about ethanol, and they're talking about getting ethanol from woody products, cellulose, switchgrass types of stuff. But the holdup there is the chemistry of turning cellulose into ethanol. And termites, again, I mean, you hated termites when you walked in. We love them now. Termites they actually have a bacteria, a symbiont in their stomach that breaks down cellulose and has a great simple chemistry to do it. So that's being looked at right now at Lawrence Berkeley Lab. Finally, removing carbon dioxide from the atmosphere. All this sequestration stuff that we're hearing about when we're talking about piping it down into rocks. Since when is carbon dioxide a poison? Plants don't think of it as a poison. It's a feedstock. It's a building block. So there are a lot of people thinking about how we might mimic how organisms, like these shells basically take carbon dioxide out of the water to create their shell. And so they've got, again, great chemistry for doing that. So this is a limestone cliff. And those diatoms, those beautiful skeletons, glassy skeletons I showed you, when they die and they get into layers, it's limestone, it's calcium carbonate, and all the other sea animals, it's calcium carbonates. Their bones and their skin, their shells. And there is a team of scientists working on taking the flue gases, taking the CO2 that's coming out of a smokestack, bubbling it through seawater with the same enzyme that the mollusks use, and then having enormous amounts of calcium carbonate formed right there at the plant. Now, we could go and mine calcium carbonate, or we could use CO2 to form it. And now they're starting to say, well, if we have all this calcium carbonate, what are we going to do with it? How are we going to landfill it? But the idea is that maybe we want to use that. Maybe we want to have this sort of an operation right at a building site. And if you're lucky enough to be near seawater, maybe you pump seawater in with a really efficient fan. You pump seawater in, and you bubble it through your power plant, and that becomes your building material on the site. Or maybe we make it a very small brick builder in a box or concrete builder in a box. Concrete right now contributes to 8% of carbon dioxide emissions because of Portland cement, because we heat it in a kiln to make it. Okay, I got one more character for you. Here is the scientist working on this. This is from her website. Okay, I found it on her website. She would have my head if she knew I was showing it. But just to let you know, these are real people behind this work. This is Jeff Coates from Cornell, and he started a company called Novomer because he figured out how to take CO2, like plants do, and turn it into polymers. In this case, he turns it into plastics, like the CDs or the sunglasses that you have. He turns CO2 and lemon juice into, this is the alchemy of our era, CO2 and lemon juice into polycarbonates, into biodegradable plastics. So what you're doing here is you're being plant-like. CO2 is not necessarily a poison if you look at it the way an organism does. The company's called Novomer. Finally, the biggest thing you can possibly do, the most important thing you can possibly do today, starting now, is just to do less with less. That's the new, you know how they always say do more with less? Do less with less. Travel less to get your stuff. Eat local food, buy local art, buy local books, for instance. Just a suggestion. This saves a lot of it saves a lot of energy, and it creates community, which you can't buy at the store. So this is a map of a food web in a coral reef. So each of the balls are an organism, and of course it's much more complex than this, but we have tiny little brains. We're trying as hard as we can. And each of these balls is an organism, and each line is a relationship, a food relationship. So imagine a little bit of food coming into this coral reef. It's not going to leave. It's going to get picked up, and it's going to get juggled and juggled and juggled in the local economy over and over and over. It's going to get eaten, and then there's going to be a little poop come out, and then this thing's going to get eaten, and those materials are going to be upcycled into another product. And that product, little poop, little heat, the materials are going to be upcycled into another product, another organism. But think about it as an economy. It's a field called industrial ecology, where you try to put your companies together in a food web, hopefully regionally, so that the raw materials of the waste of one company, quote unquote waste, is the raw material of another. And the waste heat is the energy of another. We are going pretty quickly to a bio-based economy, meaning what you're going to be sitting on. Bryony mentioned, the carpets that Interface. Interface is going to be making their carpets out of cornstarch, PLA, fermented cornstarch. And a lot of companies are going this way. And I'm sort of two minds about this. I'm very happy that we're going to be able to compost our carpets at the end of their life. That's great. But on the other hand, I realize that we've got to get really, really wise, mature, and good at agriculture. Because the new wellhead, these carpets now are made of oil. They're going to be made of topsoil. They're going to be made of soil fertility. That's the new wellhead. So we got to get really, really good at agriculture. And we have to get really good at closing the loops so they look more like that. And when you buy your carpet or you buy your bio-based product, that it doesn't go in the trash. If it goes in the trash, it's heading straight back to the farmer's field. We haven't really done those loops yet, but that's a challenge, students. Build the loops to get the bio-based products back to topsoil. There is still so much to learn. I mean, we're learning as fast as we can. Biology is doubling every 5 years, but there's still so much. So many organisms, as we speak, taking their incredibly beautiful, exquisite adaptations and folding and blinking out. What life needs in order to innovate and to evolve in an unencumbered way are wild lands. Wilderness. Lots of it. And really well managed settled lands, the ones we live in, because they use those too. So when I wrote Biomimicry, I thought about this path that started with quieting human cleverness. It's that quietude that you go out into the woods with to begin with, so that you can hear when the lessons come through. And then the second step is listening and learning to hear, learning to be a student, learning to learn from instead of just about, which is a whole different way of learning. And then the third step is echoing what you hear. It's emulating what you've heard. And that's what we've been talking about tonight. But then there's this fourth step that in many ways is the most important one, and that's giving thanks for the lesson that you were given. These are our mentors and our sensei. They're the new wise guides for us as a species. So one of the things that we're working on at Biomimicry Institute is a way to encourage companies to donate a percentage of their proceeds of these bio-inspired products to conserve habitat of the organism that inspired it. Because it's, for obvious reasons. For obvious reasons. It's just good manners. And our civilization could use a little bit, our Western industrial culture could use a little bit more of that. It's called innovation for conservation. What's worth doing? And how do you know when you're successful? Life gives us the squirrels gave us a really good idea of what to do next. Common purpose. And these guys tell us that all that matters is life, keeping yourself alive, and keeping these little guys alive, keeping your offspring alive, not in the next generation alone, but 10,000 generations from now. And the only way that they can do that is by taking care of the place that will take care of their offspring. So they create conditions conducive to life. And that's the definition of success. Have they or haven't they? Are our technologies well adapted or not? The question is, do they create conditions conducive to life? And you as students, what are you working on? Are you creating delight in the world? Are you reducing suffering in the world? Great. Think really carefully. It's going to be an important next few years. But what I want you to remember is that I think we felt like this for way too long. We're alone. We're the odd species. We're the one that can't get it right. We're different from all the other species, right? Where did we learn that myth? We are nature. Remember that you, when your heart is broken, usually every time you turn the news off, when your heart is broken, remember that you live in a competent universe and that you are part of it. And that is your home. As much as it's the home of all the other organisms that I talked about tonight, it's your home. The earth gave rise to you as well as all those other organisms. And this is our home, and it's their home. And what we have to learn how to do is to come home to this planet. And with their help, I'm really, really hoping that we can get the hang of this. And I thank you very much for everything that you're doing right now, because I don't think you'd be in this room if you weren't doing something for the homecoming. So thank you very much.
Janine is holding a workshop in May up on the Rocky Mountain front. If you're a biologist and you want to do the biologist at the design table training, I have flyers and I'll get them put up on the table over there outside. Actually, would somebody like to run up? Thanks. So if you want to do that workshop. If you want more information about the Institute, we're here in Missoula. Our website is www.biomimicry.institute.org, or you can call the office at 728-4134. And I'll just leave it at that. Thank you all very much for coming.